Today we're going to be dealing with exponential growth, which is one of the exponential functions. Exponential growth happens when a quantity increases by the same factor over equal intervals of time. Sometimes we also say that they increase by the same ratio, or also they increase by a similar percent. But what we're going to notice is that these, just like the exponential functions, are increasing by a steady multiplication of a factor. So here we have the formula. So the exponential growth formula is y equals a times 1 plus r raised to the t power. So what do those things all mean? Well, y is your final amount. A is your initial amount, or when t equals 0. R is your growth rate, which is the percent of our growth as a decimal. And t is time in years. So let's look at example 1. So how do we use this exponential growth function? Here we have a function, y equals 150,000 times 1.1 to the t power, which represents the number of people in attendance at a music festival t years after 2010. By what percent does the festival attendance increase by each year? Well, the growth factor, which is 1 plus r, is 1 plus the growth rate. And we know that from the model, this growth factor is 1.1. So if I make the equation 1 plus r equals 1.1, and I simply subtract 1 from both sides to solve for r equals 0.1. We just mentioned a moment ago that the growth rate, or the r, which we have just solved for, is always a percent written as a decimal. Well, we know that 0.1 as a decimal is 10%. So the amount that we have increased in the festival attendance each year is 10%. So the next question is, how many people will attend the festival in 2014? And they want us to round to the nearest 10,000. Well, a couple things are going to happen here. So first we'll give ourselves a little bit of space. But what's going to happen here is we have to think about the year 2014. We have the function for the attendance after 2010. So 2010 represents when t is 0, meaning that's our initial starting point. So 2014 would be when t's are 4. So we don't want to plug in 2014. We're using our starting year, which is 2010, as our base, or t equals 0, and then after that would be the number of years that we will be using this function. So then we take that information and we literally just plug in the formula. We have 150,000 times 1.1, and we're raising it to the 4th power because we're looking for the year 2014. And as I run that through the calculator, I will get 219,615. Well, we were asked to give our answer as nearest 10,000. Well, the nearest 10,000 place value is the 1. The 9 is going to make that go up. So we are going to be approximately 220,000 people who will be attending in the year 2014. Now we know that this is just a model. This doesn't mean that this will happen. A lot of things could happen that would make that number be bigger or potentially make that number smaller. But with the model that we are using, we are predicting that 220,000 people will attend. So for example 2, or 1b, I'm going to pause the video and I will give you the solution momentarily. So I would like you to Pause the video, try this one on your own, and then check back in and see if you have the right answer. So for this problem, we have the function y equals 500,000 times 1.15 to the t power, representing the number y for members of a website t years after 2010. So again, 2010 is going to be where we are representing t's are 0. So what percent does the website membership increase each year? Well, again, we would use that growth factor of the 1 plus r. It equals the 1.15. So I can solve for r to get r equals 0.15, which we know is the decimal version of 15%, which means that the membership is increasing 15% each year. How many members will there be in the year 2016? Rounded nearest 100,000. Well, again, t being 0 is at 2010, so 2016 t's would equal 6. So we're going to be raising to the 6th power, and as I plug that in, I get 1,156,530. Rounded to the 100,000s place would make that 1.1 million members. In a previous year, probably last year in 7th grade, you learned about simple interest, which was principal times rate times time equals interest, where principal was the amount of money that you either borrowed or that you put in a bank. Rate is always the interest rate as a decimal, and time is how long you left it there. And if you simply multiplied those three things together, you would find out how much interest you would make or you would be paying on a loan. Well, that is a reason that they call that simple. It's very simple, but to be honest, it's not really used anymore on any things. It is something that is interest building on the principal amount over and over again. What we use nowadays, and what is very commonly used in the business world, is something that we call compound interest. Compound interest is interest that's building on top of the principal, which is your original amount, but also all the other interest that has been earned over that same time. So it's compounding the interest versus just going back to the initial amount each time. So the formula is kind of scary looking. It's a little bit kind of complicated, but in reality it's not. And let's kind of break through the little pieces just so that we can kind of understand how it works. Compound interest really is one of our exponential growth formulas. So here we go. The y is our total final amount, which will include our principal and all the interest. The P stands for principal, which is the initial amount of money that we are either depositing or the initial amount of money that we are taking a loan on that we would be paying interest on. R, just like the growth rate, is our interest rate in this case, which is again plugged in as the decimal form. So just for example, if I had a 10% interest, I would be plugging it in as 0.1. Time is our time in years, how long we're going to be leaving it there. And N stands for the time that interest is compounded each year. So, for example, if I was to say that it is compounded yearly, then that means it's only being done once a year, so the N would become a 1. If I was to say it was semi-annually, that would mean 2 times a year, so now N's would be 2. Quarterly would be, N's would be 4, because that would be done each quarter. Monthly would be 12 times a year. So every time you compound the interest, it changes that N, which is going to change your value. So N is the number of times each year that it is being compounded. So let's look at one of these examples. So we're trying to write the function of the situation of depositing $100 into a savings account that's earning 5% annual interest compounded yearly. Okay, so the N in this case, because of that last piece there, is going to be a 1. So that's something that's important to know. So as I look at this entire formula, y is going to be 100, so the principal is our $100 deposit. The 1 plus our rate, the rate is 5%, as a decimal is 0.05. We just said the n is a 1, so we would put that over 1, we would close it, and then we're going to be multiplying 1 again, the nt, times t. Now, obviously, when I'm compounding yearly, this looks very much like the exponential growth model from the previous one, because dividing by the 1 on the inside and multiplying by the 1 times the t isn't going to change anything. So really, we put those in there just to see where they go, but in reality, 0.05 divided by 1 is still 0.05. 1 plus 0.05 is 1.05, and then 1 times t is just t. So there is the growth model to write, to figure out your balance after t years. Okay? Then let's move to the next one. So in this example, we have a deposit of $500 in our savings account where we are making 4% annual interest, and it says compounded monthly here, but I'm going to change that to compounded yearly, because I do think that that's what your note sheet says, so just ignore this. What we want to do is write and graph a function that represents the balance y in dollars after t years. So again, we want to go to our formula. We have y equals our principal, or initial deposit, is 500. We have the 1 plus the 0.04 for the interest as a decimal, and we are still compounding by 1 time a year, 1 times t years, and again that would give us the model of 500, 1.04 to the t power. So how do we go ahead and graph something like this? Well, certainly we have the graphing calculators that we can certainly try to use, but the other way to do this is we can certainly make a table. And our table would be t's representing our x's, y's would be coming out as our y values. So if I evaluate each of these when t's are 0, we will end up with $500. And again, that would make sense because t would make the 1.04 a 1, because that's our initial amount. When t's are 1, we would then get $520. When t's are 2, we're going to get $540.80. When t's are 3, we would get $562.43. And we'll go one more to 4 years, $584.93. Now, you might notice that we are changing by a little bit more than 20 each year, but I think the thing that we want to pay attention to on compound interest, if I was doing simple interest, it would change by $20 every single year forever. It would just be 20, and then 40, and then 60, and it would just be 20s forever. But if you look at the exponential model, while initially it doesn't seem to be growing by a lot, the longer it sits there, the longer that 20 is going to become $20.80, and then it's going to become $21, and then it's going to become $22, and eventually you will start seeing a more significant change. So I'm going to graph these points, and then I'll come back and show you what the graph would look like. And so your graph would look something like this. And again, because right now at the earlier years, it does kind of have a little bit of a straight line look. These are not a linear equation or function. So while it might look that way initially, as time goes on, when we get to 15, 20, 30 years, the exponential curve would show more and more. But for now, this is what we would start with these early years. So for our last example, here we have something we're working a little bit backwards for. We have a table of values, and we are asked for finding the function where we actually have the balance already. We know what the y's are coming out as. And what we have to do is kind of work backwards to figure out, well, how are these numbers changing, and where do I find this rate or this growth factor that we are working with? Well, one way to do this is to take my numbers. So, for example, if I look at the 100 and the 110, so I'm going to come down here a little bit, and if I was to say 110 divided by 100, I would get a 1.1 growth factor. Okay? If I then moved on to this one here, I would have 121 divided by now 110, and I'm also going to get a 1.1 multiplication difference or factor difference. So one of the ways that we do this when we have this data, we want to try to figure out, well, how are these numbers changing from one to the next? And one way to do that is to kind of go further ahead, divide the one previous to it to help find what is the factor that got me from the first one to the second one. And really what we're doing is working on a percent change at this point. So 1.1 seems to be what my growth factor is. So if I write my function for this, y equals our initial amount, which is what we are going to be referring to as our A. Our A amount is 100, so the A plugs in as 100. Well, our 1 plus R, the 1 plus R we just figured out is 1.1, and the T has to remain a T until we know how many years we're talking about. So there's the function to find the balance after T years. So certainly we could have kept saying times 1.1 times 1.1 to get to, for example, 10 years. Or now that I have the model, I could plug in 10 for the exponent and solve it that way. So now we want to graph the function. And again, when you're graphing the function, we already have a table in this point, so this one should be a little bit easier. So I'm going to pause the video and show you what the graph is going to look like. If you could just do the same thing yourself and give yourself a chance to see how it comes out. So you should have something that looks like this. Notice that on my scale I went up by 5s really, but I started at 100. I skipped by half years basically to stretch out my horizontal x-axis a little bit. And again, I know initially this kind of looks like, well, it's very close to being a linear equation, but again, we've just kind of proved that it's not a linear equation because I'm not adding a constant rate of change. I'm not going from 100 to 110 by plus 10, because then it would be 110 to 120, which is another plus 10. This is definitely not a linear equation because we don't have a steady rate of change. What we are changing by is a steady rate of a factor of change. So there you have exponential growth functions. I think the thing to keep in mind and to notice when we talk about the other type, exponential decay, is when you look at the exponential growth model, what you're going to notice is that growth factor, which is the greater than 1 number that is being raised to that t power, is allowing that number to continue to grow. The 1 is representing 100% of what you have, and the decimal next to it, in this last case, the 0.1, is telling us that we are taking that 100% and we are going to go up 10 more percent each time thereafter. So the exponential growth function is this one right here. Again, it's very similar in a lot of ways to just the exponential functions, but it's obviously a more specialized one. And good luck with the practice, and we will talk to you again about the exponential decay in our next lesson.